Hi everyone, this is Kaushik, working as Assistant Professor in EC Department from MLR Institute of Technology, Hyderabad. In today's session, we're going to discuss about Digital System Design subject. In that, we're going to cover a topic, number system and its conversion. And in today's session, we're going to cover what is a number system and how many types of number systems are there and what are the possible different conversions are there in these number systems. So we're talking about what is a number system and how many types of number systems are there, and we're also trying to cover conversion of one radix to another radix, that is one number system to another number system. Okay, let's come back to this one. Firstly, what is a number system? Number system is basically used for representing a number which does has set of digits or set of numbers which predefined roles and to perform specific operation or specific arithmetic operations. Okay, now coming back to the types of number systems. Types of number systems, there are four possible different number systems that we are utilizing in our DSD subject, and those are binary, decimal, hexadecimal, and octal. These are the number systems that we are utilizing in our DSD subject. And coming to the conversion of one radix to another radix, with these four possible number systems, we can able to create 12 different types of conversions, and we will do that. We will do those conversions also. Okay. Now let's look into the what is actually a number system. In a number system, we do have a number as well as its base value. For example, if I take this value n, if I represent a number and this n represent my number and this value, this value represents my base or radix. The number may contains integer part as well as it also contains fractional part. If you here I took an example. In this total part indicates integer part and this entire part indicates fractional part. Remember one thing, in number each and every digit holds certain value depending on its positional value. Okay, depending on its positional weightage. If a number contains positional weightage, then such kind of number system called as weighted number system, and if it doesn't have any kind of positional weightage, then such kind of number system called as unweighted number system. Okay, if you look into this one, for example, my base value is here, it is r. Here the base value is represented as r. For that one, for this digit, I can indicate its base value as base to the power 0, base to the power 0, and here I can write this one as base to the power 1. In the similar way, here I can write this one as base to the power 2, and here base to the power rn minus 2, and so on. I can write like that. Here for this d minus 1 bit, I can write its base value as r power minus 1. For d minus 2 bit, I can write this positional weightage as r power minus 2, and similar way I can write this one r power minus n. And these all are possible positional weightages with respect to the number system. Here r represent base. For example, binary, in case of binary, its base value is 2. That means its positional weightage value varying with respect to the digits positions. Here r power 0, that means in case of binary it is 2 power 0. In case of decimal, the base value is 10. In that case, it will be 10 power 0, 10 power 1, 10 power 2, like that. For example, if you consider a number, likewise I am saying decimal number system. Decimal number system is our day-to-day life number system. We are utilizing in our day-to-day life. Okay. For example, if I consider a number 143, okay, here it is, its base value is 10. Okay. In that case, for this digits, the positional value, usually we will call that one as ones position. We will call that one as ones position, and here it is tens position, and here it is hundreds position. How exactly we calling this one? If you look into this one, this bit positional value or positional weightage is r power 0, right? R power 0 means here the base value is 10 power 0. 10 power 0 automatically it is 1. 10 power, here it is 10 power 1, and again it is equivalent to 1 on 10 only. Here it is hundreds position, right? In that case, it is 10 square. 10 square is again 100. In this way, we are defining its positional values. Okay. let's look into the types of number system. In types of number system, we are basically utilizing 4 number systems here. One is a binary here, binary, and another one is a octal, another one is a decimal, and another one is a hexadecimal number systems. These are divided depending on its base value. For example, if you look into the binary, its base value is 2. Its base value is 2, and it does have two different digits. Okay, that means in generally, if you consider a number, its base values we are considering in generally as r. That means for each and every possible number system, we're going to have r different digits. And the value of these digits are varying from 0 to r minus 1. For example, here first value is 0 and r minus 1, the base value is 2. 2 minus 1, it is 1. That means the binary does have unique digits as 0, 1. In case of octal, the base value is 8. That means it does have 8 different unique digits. And those values are starting from 0 and up to 7, like 0, 1, 2, 3, 4, 5, 6 and up to 7. In case of decimal, the base value is clearly it is 10. That means it holds 10 different unique digits, and the starting value is from 0 to up to 9. In case of hexadecimal number system, the base value is 16. Remember one thing, base is also called as radix. Okay, we are supposed to have 16 different unique digits, and this hexadecimal number system also called as alphanumeric number system. It is also called as alphanumeric number system. Okay, that's why as the name itself alphanumeric, that means it does contains alphabets as well as numerical values. It starts from 0 to 9 and A to F. 0 to 9 and A to F. These are the different types of number systems. Let me tell you one more thing. If I consider generally, let's consider one general number system. I'm considering here binary number system 1001 with a base value of 2. Okay, we talked about positional weightage, right? In that case, we can able to define one more thing, that this positional value, this digit is the holding least positional value. That means this bit can also be called as LSB. You can call this one as least significant bit because it holds the least positional value. And according to given this problem, we can say that this is the bit which holds maximum positional value. So you can call this bit value as MSB, most significant bit. Okay, next coming to the conversions. As I already told you that we're going to have 12 different types of conversions with possible basic number systems. Okay, in that I'm trying to cover the first topic, that is our decimal to any radix number system, which itself covers almost 3 different conversions. For example, right now I'm saying that decimal to any radix. Any radix means we spoke right now 4 different number systems. Out of that, if I take decimal from, we are converting decimal to another radix, and the remaining radix values are binary, octal and hexadecimal, right? That means these are the types of conversion that we are trying to look into right now. Okay, let's jump into the topic. Next one here, decimal to any radix number system. Just now I said that we can able to convert into binary, octal as well as hexadecimal. Here I am considering a simple problem. Convert 25.625 with a base value of 10 to an equivalent binary. Now let's consider this number 25.625, base value of 10. Now look at the number. This number contains integer part as well as fractional part, and this dot is called as radix point. This point is called as radix point. Okay, now look at this one. Here, whenever you're trying to convert from decimal to any other radix, always remember you are supposed to divide integer value with base. For example, this is my number, some number is there. Here I am trying to convert into some other radix or that means the integer part, this integer part should be divided by this base value r. Okay. In case of fractional part, you are supposed to multiply that fractional value with respect to this base r. Here we are having both values, integer as well as fractional. Let's try to convert that value. In case of integer, what I said, we are supposed to divide here. That means let's consider the integer part only, 25. Now what is the base value that we are trying to convert, binary, and its base value is 2. That means you are supposed to divide the integer part 25 with 2 as long as the remainder value, remains below 2. Okay, let's divide 2, 25, 12 2s are 24, and the remainder is 1 here. You need to continue the division till the value reaches to the less than 2. Okay, 12 2 6 are 0, 2 3s are again the remainder value is 0, 2 1s are 1. Here the value is less than 2. You can stop it here. Okay, now let's focus on the fractional part. I will tell you how to copy the value or how to write the equivalent binary value. Now let's focus on the fractional part. 0.625. We are supposed to multiply, right? Just now I said if you are converting a fractional part into another radix, in that case you are supposed to multiply with its base value. Here the base value is 2 here. 0.625 into 2, the resultant value is 1.250. In that case, copy this value separately, keep it aside. Now the remaining value is 0.250 and again multiply with base value 2, and the resultant value is 0.50, and again copy this value and keep it separately. Now look at the remaining value, 0.50 into 2, that is 1.00. Copy this value. Okay. Now here, after that I'm remained with only all 0 values. I don't need to multiply that value. So now look at this. In case of integer part, we already done that part division. Now if you're trying to convert this entire value into its equivalent binary from decimal to binary, in that case simply in case of integer part, write the values from down to top. In case of integer part, that is 11001. This is the value for 25, and the remaining value is fractional part, that is 0.625. In that case, you are supposed to copy the value from top to down. The value is simply 101. Total value. In this total value is equals to its 25.625 in terms of decimal. Okay. Now this is just decimal to binary. Let's look into the another example. Let's consider one number randomly. For example, if I am considering a number 469, let's consider number system as 10. Given the number system is 10, now we are trying to convert that into an equivalent octal number system. Okay, in that case you are supposed to divide this integer part with respect to what? 8 only. That's what exactly we discussed just now, right? In that case, consider the 469 and divide with 8. 8 5s are 40, remainder is 6. 8 5s are 40 and the remainder is 6. 8 8 just 64. 8 8 just 64. Remainder value will be 5 here. Right. Next 8 7s are 56 and the remainder is 2. And I can't divide this 7 with respect to this 8. So we can stop the division here. Now what I said, in case of integer part, always write the values from down to top. That means my equivalent value of this 469 in terms of octal number system is 725. Okay, in this way you can able to convert from decimal to other remaining radix numbers. Simply you are supposed to do is division for integer part. In case of fractional part, you are supposed to do the multiplication. In case of integer part, you are supposed to note down the resultant values from down to top. In case of the fractional part, you are supposed to note down the resultant values from top to down. Okay, let's look into the another type of conversion. Okay, and that is any radix number system into decimal number system. What is the meaning of any radix here? Any radix means we are having, I discussed that we are utilizing only 4 types of number systems. Any radix to decimal. Decimal itself covers 10, base value 10, and the remaining values are 2, 8 and 16. 2, 8 and 16. That means we are trying to convert these types of the number system into its equivalent decimal value. In that case, remember only one thing, you are supposed to multiply each and every digit with its positional weightage, then you are supposed to add them to get the equivalent decimal value. Okay, you are supposed to do what? You are supposed to multiply each and every digit with its positional weightage. Okay, in here, my base value is 2 here. For example, let's write it again. The problem, given problem is 1001.101. You need to convert this binary value into its equivalent decimal value. To do that, what I'm supposed to do? Multiply each and every digit with its positional weightage. Okay, here it is my fraction point or the radix point. To the left side, the positional weightage is base to the power 0. Base to the power 0. That is my positional weightage, right? With respect to this specific digit, right? Here, its positional weightage will be 2 power 1. Here, its positional weightage will be 2 square. And here, its positional weightage will be 2 cube. Okay. To the right side of the radix point, I already said this in the beginning of the session. That is 2 power minus 1. Base value to the power of minus 2. Base value to the power of minus 3. To convert any radix number system into its decimal number system, simply multiply each and every digit with its positional weightage, then perform the addition. Let's look into that. 2 cube positional weightage multiplied with respect to its digit value, that is 1 into 2 cube plus again digit into its positional weightage, 2 square plus 0 into 2 power 1 plus 1 into 2 power 0. Up to this part, it is integer part. And again, let's look into the fractional part. That is 1 into 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3. Okay, 1 into 2 cube, that is clearly 8 plus 0 plus 0 plus 1 into 2 power 0, it is 1 point. And 1 into 2 power minus 1, that can be written as 1 by 2, and the value will be 0.5. The value will be 0.5 plus 0 into any value, it becomes 0. And 1 by 2 cube, that is 1 by 2 cube means 1 by 8, with the resultant value will be 0.125. The total resultant value of the fractional part will become 0.625. The total value of integer part will become 9. The entire value can be represented as 9.625 in terms of decimal, and this is the equivalent decimal value for the given number. Okay, now let's take the another example. Just now we converted here 469 given in terms of base and 725 into its equivalent octal value. Let's try to convert in the reverse approach. Like 725, this time we are taking the example as 725 as given in the octal number system. Now we need to find its decimal number system, its equivalent decimal number. Let's check it out whether we are getting the right answer or wrong. Okay, now in case of what is the base value here? Here it is 8, right? Now what we are supposed to do, multiply each and every digit with its positional weightage, then you are supposed to perform the addition, right? Let's look into this. What is the positional weightage here? 8 over 0. Here it is, the given number is clearly contains only integer part. In that case, it is 8 power 0. And for this, the positional value is base power 1, and here it is base power 2, right? Let's do the multiplication, then perform the addition. Okay, 7 times of 8 square plus 2 times of 8 power 1 plus 5 times of 8 power 0. Okay, 8 square, that is 64. Okay, let's write it again. 64 plus 2 times of the 8, 16 plus 5 times of the 8 power 0. 8 power 0 is 1. 5 times of the 1, and the resultant value is 5. Okay, 7 4 is 28, 7 6 is 42. Totally, the resultant value will be 448 plus 16 plus 5. If you perform the addition, the resultant value clearly 469, and this is represented in terms of decimal number system. In this way, you can able to convert any radix number system into decimal number system. Okay, thank you.